Imagine a typewriter sitting in the corner of a room. Now imagine a monkey placed in front of it, pounding randomly on the keys. At first, all you get is nonsense, strings of letters without meaning. But the thought experiment doesn't stop there. Suppose the monkey keeps typing, not for an hour, not for a lifetime, but for eternity. The question is, what will eventually appear on the page? The strange answer is that, given infinite time, the monkey will produce every possible combination of letters. Somewhere among the endless nonsense will be every poem, every novel, every sentence ever written. In fact, tucked inside the chaos will be perfect copies of every book on earth, from the works of Shakespeare to the one you're holding in your hands right now. All of it would eventually emerge, simply because infinity has no limit to what it allows. This is known as the infinite monkey theorem. At first, it feels like a joke, but the point is serious. It shows how infinity makes even the most improbable outcomes inevitable. The chance of a monkey typing Hamlet by accident is unimaginably small, so small that if you tried it for 1 billion years, you'd likely see nothing but gibberish. But stretch the time to infinity, and even the rarest possibility must appear. The unsettling part is not the monkey, but what this says about probability. In an infinite span, probability collapses. Anything that can happen, no matter how unlikely, is guaranteed to happen. Not once, but infinitely many times. The monkey won't just write Hamlet, it will write it again and again and again, hidden among an endless ocean of nonsense. To make the idea clearer, think about shuffling a deck of cards. There are so many possible orders that if you shuffled for a lifetime, you'd almost never repeat the same one twice. But if you shuffled forever, every possible order would eventually appear. One day, the deck would fall into perfect ascending order, from ace to king. Another day, it would fall into reverse. Every sequence would show up, given infinite tries. The infinite monkey theorem takes this same logic and applies it to language, art, and meaning. It tells us that infinity does not just stretch time, it stretches possibility. And in doing so, it forces us to rethink how we talk about chance. But there's a hidden irony here. Even though the theorem says every masterpiece will eventually appear, they would be drowned in an ocean of random nonsense. For every page that makes sense, there are trillions upon trillions that do not. So while infinity guarantees Hamlet, it also guarantees every possible typo, every garbled version, every page of meaningless text. The rare jewels of meaning are buried beneath endless noise. Some people see this as a metaphor for the universe. If space and time are infinite, then everything that can happen will happen, and will happen endlessly. Somewhere there may be a world identical to ours, another where things turned out slightly different, and another where they turned out unimaginably strange. The theorem suggests that infinity contains not just what is real, but everything that could ever be real. For most listeners, what sticks is not the math, but the image, the absurd sight of a monkey hammering away at a keyboard, with Shakespeare slowly emerging from the chaos. It's a comic picture, but also a haunting one, because it shows how little probability means once infinity steps in. And maybe that is the lesson worth keeping. Infinity does not just open doors, it opens every door, whether you want it to or not. It guarantees brilliance and nonsense, beauty and madness, side by side. It reminds us that infinity is not about certainty or order. It is about inevitability, the certainty that, given endless time, everything possible will unfold. Close your eyes for a moment and think about the world around you. You take it for granted that the room you sit in, the body you inhabit, and the memories you carry are all part of a continuous life. But now, imagine a darker possibility. What if everything you see and remember is nothing more than a random fluctuation, a temporary pattern formed out of chaos? What if you are not the result of history, but a mind that appeared by chance in the endless sea of infinity? This is the idea of the Boltzmann Brain. Named after the physicist Ludwig Boltzmann, it begins with the notion that in an infinite universe, or in a universe that lasts for infinite time, every possible configuration of matter will eventually occur. Given enough time, atoms will arrange themselves into stars and galaxies. Given more time, they will arrange themselves into planets and people. And given still more, they will, by sheer accident, form a brain, complete with memories, sensations, and the illusion of a past that never happened. If the universe is infinite, then Boltzmann brains are not rare accidents. They are inevitable. Not only will they exist, but there will be infinitely many of them. Each one will believe it has lived a long life, formed relationships, learned lessons, and experienced the world. Each one will feel as real as you do right now, and yet, outside its momentary spark of thought, there is nothing. No body, no history, no world, just a fragile pattern that dissolves almost as soon as it forms. The paradox cuts deeper when you ask, how do you know you're not one of them? Every memory you have could, in principle, be a fabrication of this moment, stitched together by chance. Your entire past, your childhood, your friendships, the years of living you believe you've experienced, could be nothing more than a convincing illusion. If Boltzmann brains vastly outnumber ordinary observers, then statistically, it is more likely that you are one of them than that you are a being with a genuine history. The origin of the idea lies in thermodynamics, in the study of disorder and entropy. Over infinite time, even the most improbable events are not just possible, but certain. A cup of coffee may never spontaneously reassemble itself after spilling, but in an infinite universe it will. And if a cup can, so too can a brain, complete with a fabricated memory of spilling that coffee in the first place. What makes this scenario difficult to dismiss is that it does not violate the laws of physics, it arises from them. If the universe stretches forever, then probability demands that everything that can happen will happen, and will happen endlessly. Consciousness is just another arrangement of matter, and so it too must emerge, again and again, in forms both genuine and counterfeit. For some, this idea is unbearable. If it were true, then reality itself would lose its stability. You could never be certain that the world existed before this very moment. You could never know that the memories you trust are genuine. Infinity would strip meaning from experience, reducing life to a flash of thought floating in the void. Others take a different view. They argue that the very fact we can ask these questions suggests we are not Boltzmann brains. A fleeting mind, appearing by accident, would not have the coherent structure required to reflect on itself. The stability of our world, the continuity of our science, the persistence of shared experience, all of these are evidence that we are more than statistical phantoms. Still, the doubt remains, in an infinite cosmos, how do we separate the real from the accidental? How do we prove that our history is not an illusion, when any illusion can be made perfect by infinity? The image of the Boltzmann brain stays with us because it is not just a scientific puzzle, but an existential one. It asks whether we can ever be sure of our own reality, or whether infinity itself will always leave the door open to doubt. That is the paradox of the Boltzmann brain. Infinity does not just expand the universe outward into galaxies beyond number. It turns inward, pressing against the foundations of identity itself. It suggests that even consciousness, the one thing we feel certain of, may be nothing more than a temporary accident in an endless sea of chance. And it leaves us with the sobering thought that the self we know may not be a product of history, but a flicker of order that will soon dissolve back into chaos. Every explanation begins with a question, and every question seems to demand an answer. But what if each answer only opens the door to another question, and that question to another, without ever reaching an end? This is the shape of an infinite regress, a chain of reasoning that stretches backwards without a foundation. Consider the classic riddle of causation. You ask why something exists, and you're told it was caused by something else. You then ask what caused that cause, and the answer points to another. Push the inquiry further, and you're sent back again, step by step, into a sequence that never resolves. If everything must be explained by something before it, then the chain has no first link, and the explanation dissolves into infinity. This is not only a problem for philosophy, but for everyday thinking. Imagine trying to understand why a rule is in place, and being told it rests on another rule, which rests on yet another. If each justification requires a further justification, you find yourself caught in a spiral with no bottom. It feels like standing on a staircase that descends forever. Each step is solid beneath your feet, but there is never a ground floor. Different thinkers have tried to escape the regress in different ways. Some argue that the chain must eventually stop at a foundation, a first cause, an unmoved mover, a principle that explains itself. Others claim that infinite regress is not a flaw but a feature, that explanations can stretch endlessly without requiring a beginning. Still others say that certain questions cannot and should not be pushed that far, because the demand for absolute justification is itself unreasonable. The difficulty of infinite regress lies not in its complexity, but in its simplicity. It takes the most natural impulse to ask why and pushes it until it breaks. If every why leads to another, then meaning itself begins to dissolve. The world remains, but the ground beneath our reasoning crumbles. You can feel the pull of regress in countless areas of thought. In ethics, when every moral rule seems to depend on another, until no absolute law is left standing. In science, when every explanation is built on deeper assumptions that demand their own explanation. Even in ordinary conversation, when a child asks why, and no answer seems to finally satisfy. The regress is always there, waiting at the edge of inquiry. Infinity is what gives it its peculiar force. With a few steps, regress is manageable. You can trace causes back through history or rules back through logic, but stretch the sequence beyond every boundary, and you're left with a void, a descent without anchor. Infinity does not just extend the chain, it makes the absence of a foundation inescapable. And perhaps that is why regress feels so haunting. It suggests that beneath our explanations there may be nothing but more explanation, an endless mirroring that never reaches bedrock. We long for certainty, but regress offers only the reflection of reflection, a hall of mirrors with no exit. The infinite regress is not a puzzle to be solved with clever tricks. It is a reminder of the limits of explanation itself. It shows us that infinity does not always appear in numbers or shapes, but in the very structure of thought, in the way questions can chase one another forever. And maybe the deeper point is this. When we reach the end of an explanation, what we truly face is not always a final answer, but the decision to stop asking. The regress will always invite us further back, always offer one more why. Whether we resist or surrender, infinity waits in the silence between questions, pulling us toward a depth that never ends. Imagine a hotel that stretches endlessly. Each door is marked with a number, beginning at 1 and continuing upward without limit. No matter how far you walk down the hall, there is always another room ahead of you. Now picture this. Every single room is occupied. By ordinary rules, the hotel is full. No vacancies, no space left. But this is no ordinary hotel. It exists only in the imagination, a thought experiment created by the mathematician David Hilbert to show how infinity behaves in ways that seem impossible. Suppose a new guest arrives at the door. The hotel is full, yet the manager doesn't turn them away. Instead, every person already inside moves down one room. The guest in the first room goes to the second. The guest in the second goes to the third. Each person shifts forward, making room at the front, and suddenly, what was once completely full now has space for one more. Now imagine a bus pulls up with 50 passengers. It sounds hopeless, but again, the hotel adapts. Every current guest moves 50 doors further down the hallway. What had been the first 50 rooms are now empty, ready to take in the new arrivals. And then comes the true test. An endless bus arrives, carrying an infinite number of people. Surely no hotel could handle that. Yet the manager still finds a way. Each guest already inside doubles their room number. The first guest moves into room 2, the second into room 4, the third into room 6. All of the even-numbered rooms become occupied, leaving every odd-numbered room open. And since there are infinitely many odd numbers, there is now enough space for the entire endless busload of new guests. This is the essence of Hilbert's hotel. Infinity does not behave like a very large number. It follows its own strange logic. A hotel with 100 rooms can only hold 100 people. A hotel with 1,000 rooms can only hold 1,000. But a hotel with infinitely many rooms can be completely full, and still never truly full. Our ordinary words, full, empty, crowded, vacant, lose their meaning here. Hilbert invented this story to show how uncomfortable infinity is for the human mind. We're used to limits. We can count objects, measure distances, keep track of what's possible and what isn't. But infinity slips out of that frame. It allows things that sound absurd. A full hotel that always has more room. The idea may sound whimsical, but it touches serious questions. If the universe itself is infinite, does the same logic apply? Could a cosmos already filled with galaxies, stars, and events still have room for infinitely more? And if everything that could happen does happen infinitely many times, then how do we even talk about chance or probability? What does it mean to say something is more likely if every possibility occurs endlessly? Hilbert's hotel isn't real, but once you picture it, it's hard to forget. You can see the endless hallway, the shuffling guests, the manager calmly finding space where there should be none. A place that is full and yet never full. And in that strange image lies the lesson. Infinity is not just a bigger number hiding somewhere beyond our reach. It is a different kind of reality altogether. And Hilbert's hotel is the doorway that lets us glimpse it. Picture an endless line of prisoners, each wearing a hat that is either black or white. They cannot see their own hat, but each can see every hat worn by the people standing ahead of them. One by one, starting from the prisoner at the very back, they must announce the colour of their own hat. A wrong answer costs their life. A correct answer allows them to live. At first, the challenge looks hopeless. The prisoner at the back seems to know nothing about their own hat, and the further forward you go, the less information anyone seems to have. With infinitely many prisoners, the setup feels like a grim exercise in chance, where most are bound to fail. And yet infinity provides a surprising escape. Before the guessing begins, the prisoners are allowed to agree on a strategy. With a clever plan, they can arrange it so that at most one prisoner will die, while every other person in the infinite line will survive. The method relies on something subtle. The prisoner at the back, the one who speaks first, uses their guess not to save themselves, but to send a signal to everyone else. They look down the line and consider the entire infinite pattern of hats. Instead of announcing what they see on their own head, which they cannot know, they say a word that encodes information for the others. One version of the strategy uses a simple idea, evenness and oddness. The last prisoner counts the number of white hats they see in front of them. If that number is even, they say white. If it's odd, they say black. Their own fate is a coin toss, but the word they speak carries meaning. The next prisoner listens to that clue. They can see the hats ahead and they now know whether the total number of white hats is even or odd. With those two pieces of information, they can deduce the colour of the hat on their own head with certainty. After making their announcement, the prisoner in front of them uses the same reasoning, and the pattern continues forward, down the infinite line. The result is astonishing. Only the very last prisoner may be lost, yet every other one, infinitely many of them, is guaranteed survival. What seemed like a hopeless puzzle turns into near total victory, all because infinity makes it possible to spread information across a sequence that never ends. This scenario reveals something important about infinity. In a finite group, the same approach would only save some portion of the prisoners. There would always be a sharp limit to how far the strategy could reach. But with an infinite line, the rules bend. Certainty can be hidden inside uncertainty, and information can be carried across the entire chain without running out. It also leaves behind an eerie thought. In this puzzle, infinity acts like a shield, protecting nearly everyone while demanding only a single sacrifice. It creates a situation where survival is distributed in a way that defies ordinary fairness. One dies infinitely, many live, and the balance feels almost supernatural. The image of the prisoners calling out their guesses one by one lingers long after the details fade. You can almost hear the voices echoing forward, each answer preserving a life, the lines stretching into the horizon. It is a haunting scene, one that captures both the cruelty and the strange generosity of infinity. The infinite prisoner's paradox is not really about hats or punishment. It is about how infinity transforms the very structure of logic. It takes a problem that looks unwinnable and flips it upside down, revealing an escape hidden in plain sight. And it leaves us with a reminder that when infinity is involved, what seems hopeless may carry a solution, waiting in the endlessness to be found. In everyday life, we're used to a simple rule. If you cut something into pieces and put those pieces back together, you end up with the same amount you started with. Slice a loaf of bread into 10 pieces, it's still one loaf of bread. Chop a log into firewood, you don't get more wood, you just get smaller chunks. But in mathematics, there is a strange result that defies this common sense. It's called the Banach-Tarski paradox, and it says that under certain conditions, you can take a solid ball, cut it into a small number of pieces, move those pieces around, and end up with not one ball, but two balls, each the same size as the original. In other words, something is created out of nothing. The idea was first published in the 1920s by two mathematicians, Stefan Banach and Alfred Tarski. They were working in the abstract world of set theory, where shapes are not made of atoms or matter, but of infinitely divisible points. And within that world, something bizarre happens. Those points can be grouped and rearranged in ways that are impossible in the physical world. Here's one way to picture it. Imagine you have a perfect sphere, like a polished marble. Instead of carving it with a knife, imagine you can split it into a handful of incredibly strange pieces. Not slices in the way you'd cut an orange, but twisted, scattered fragments, each made up of infinitely many points. These pieces are so counterintuitive that you could never hold or see them, but mathematically, they are well defined. Now comes the strange part. If you take those fragments and rotate or move them in just the right way, they can be reassembled into two complete spheres, each identical to the original. No stretching, no adding new points, only rearrangement. You start with one ball, you end with two. Of course, if you try this in real life, nothing like it will happen. Cut a basketball into pieces, and you just have a ruined basketball. The paradox only works in the realm of pure mathematics, where space is thought of as infinitely detailed and perfectly divisible. It relies on a property called the axiom of choice, a rule in set theory that allows you to select elements from infinite collections. With that axiom, the impossible becomes possible. The Banach-Tarski paradox has unsettling implications. If physical matter truly behaved like the mathematical points of a sphere, then in principle, one could take an orange, divide it in this peculiar way, and end up with two oranges identical to the first. Do it again, and you could fill a whole basket. from a single object, an infinite supply. Naturally, this does not happen in the real world. Matter is made of atoms, not infinitely divisible points, and the laws of physics prevent the kind of rearrangement the paradox describes. But the very fact that the mathematics works out this way shows the strange consequences of combining infinity with geometry. Some see the Banach-Tarski paradox as a curiosity, a mathematical magic trick. Others view it as a warning sign that infinity, when pushed too far, produces results that no longer make sense in reality. It tells us that the rules we rely on in the physical world, rules about conservation, about cutting and reassembling, cannot always be trusted when we deal with infinite sets. So what does this leave us with? A puzzle that sits between wonder and unease. In ordinary life, something cannot come from nothing. In the Banach-Tarski world, it can. One sphere becomes two, without adding a single new point. And that is the unsettling beauty of infinity in mathematics. When logic allows it, the impossible becomes inevitable. Imagine a lamp in a room with a simple switch. You decide to play a strange game with it. At the very start, you flip the switch and the lamp turns on. A moment later, you flip it back off. Then you flip it on again, only this time you don't wait quite as long. Then off again, with an even shorter pause. Each time the gap between flips gets smaller, and the switching grows faster and faster, almost like a drumbeat speeding up. By the end of the minute, the pauses have become so tiny they vanish into nothing, and the switch has already been moved back and forth an infinite number of times. In just one ordinary minute of time, you've carried out a task that should be impossible, finishing an endless sequence of actions. By the time one full minute has passed, you will have flipped the switch infinitely many times. The question is, what state is the lamp in at the end of that minute? Is it on or off? This puzzle is known as Thomson's lamp, after the philosopher James Thomson, who proposed it in the 1950s. At first, the question seems simple. It has to be one or the other. But when you think about it carefully, the problem collapses. There is no last flip, because the sequence never ends. Every time you think you've reached the final move, another one is waiting. The lamp is caught in an infinite chain, and so we can't say with certainty whether it's glowing or dark when the minute is up. On one level, the paradox exposes how strange it is to imagine infinity compressed into a finite span of time. Mathematicians call this a supertask, completing infinitely many actions in a bounded interval. The mind can picture it, but logic stumbles over the result. If you lean towards saying the lamp must be off, you can argue that every time it's turned on, it is eventually switched off again. But the opposite argument is equally strong. Every time it is turned off, it is eventually switched back on. Neither outcome dominates the other. Both have the same claim, which leaves us nowhere. And yet the sequence is perfectly clear at every step. Flip after flip, the lamp obeys. What breaks down is not the process, but our attempt to describe the end. We ask for a final state where none exists. Infinity, squeezed into 1 minute, refuses to deliver a neat conclusion. Philosophers have debated what this means. Some argue that Thomson's lamp shows supertasks are impossible in reality. The physical world cannot perform infinite actions in finite time, so the paradox is only a warning against taking infinity too literally. Others argue it reveals a gap in our logic, that not every question has a definite answer, and sometimes on or off is the wrong kind of choice to demand. The paradox also resonates with physics. In quantum mechanics, particles sometimes behave in ways that seem undecidable, caught between two outcomes, until measured. Thomson's lamp is not the same thing, but it echoes that discomfort. It shows how quickly the ground shakes beneath us when infinity enters an everyday situation. For most people, what makes the lamp so eerie is its simplicity. It doesn't ask us to understand advanced mathematics. It asks us to imagine flipping a switch faster and faster until the act of switching dissolves into the impossible. The lamp becomes a symbol of how infinity hides inside the ordinary, and so the lamp remains a puzzle without resolution. At the end of the minute, we are left staring into the silence of the room, unsure whether it is lit or dark. The paradox is not in the lamp itself, but in our attempt to force infinity into a box that was never meant to hold it. That's the lesson Thomson left us. Infinity is not just large, it changes the very nature of the questions we can ask. Sometimes the problem is not that the answer is hidden, but that the answer may not exist at all. And maybe that is what makes this paradox linger. It reminds us that our categories, on and off, yes and no, certain and uncertain, can fracture in the presence of infinity. And when that happens, even a simple lamp can leave us in the dark. A dartboard looks harmless enough. A simple circle divided into regions, each waiting for a dart to land. But once infinity enters the picture, even something as ordinary as this game of chance begins to twist into something strange. The puzzle begins with a single throw. You stand at the line, take aim, and send the dart flying. It strikes somewhere on the board, as expected. But then comes the question that changes everything. What are the odds of hitting any exact point on that board? Not a region, not a slice, not even a square you could actually see, but a single mathematical point. The answer is unsettling, because the chance of hitting that one point is zero. Not just small, not unlikely, but zero exactly. And yet, when the dart lands, it must land somewhere. It cannot avoid all of the points because there is nowhere else for it to go. Every individual point is impossible, but one of those impossibilities always happens. This is the infinite dartboard paradox, and it sits at the crossroads of geometry, probability, and infinity. It forces us to confront a gap between the way we talk about chance in everyday life and the way chance actually behaves when stretched across infinite detail. Think of it like this. The dartboard holds infinitely many points, each one so small it has no area, no measurable size at all. Probability depends on comparing sizes, the area you want against the total area available, but a single point has no area to compare, so its probability collapses to zero. And still, every dart that has ever been thrown, or ever will be thrown, ends up on one of them. Infinity makes certainty and impossibility exist side by side, and that's why the dartboard feels so strange. In daily life, a probability of zero means something will never happen. If your chance of winning the lottery is zero, you won't win. If the chance of rain is zero, you don't bring an umbrella. But here, a chance of zero does not mean never. It means inevitable. The picture only grows stranger when you zoom in. Imagine looking closer and closer at the spot where the dart lands. However far you go, you never reach the smallest piece. Every region contains infinitely many points. Zoom in again, and there are still infinitely many more. No matter how deep you look, the detail never runs out. The dart has not just hit the board, it has collided with infinity. And yet, the math gives us a way forward. Probability can be assigned to areas, but not to individual points. If you take a slice of the dartboard, no matter how thin, the chance of landing somewhere inside it is real and measurable. But when you break that slice into the points that compose it, every one of them carries a probability of zero. Probability vanishes in the details and only reappears when the details are gathered back into regions. This reveals the deeper lesson of the paradox. Probability, which feels so steady in daily life, depends entirely on how outcomes are grouped. Infinity exposes that dependence. Treat the dartboard as a collection of points, and everything is impossible. Treat it as a collection of regions, and everything makes sense again. Infinity forces the rules to change, depending on the perspective you take. And maybe that's why this paradox lingers. It takes something familiar, a dartboard, a pub game, a throw of the hand, and reveals a hidden structure that undermines our intuition. You can throw a dart, land on a point, and know in the same instant that the outcome was both impossible and guaranteed. That is the infinite dartboard paradox. It tells us that zero does not always mean never, and that certainty can be built from impossibility. It shows us that even the simplest throw contains an infinite puzzle, one that turns a game of darts into a reminder of just how slippery infinity really is. Picture yourself stepping into a lottery hall where the rules feel completely unfamiliar. Instead of a few million tickets, this lottery prints infinitely many. Each ticket carries a number that stretches higher and higher without end. You take one, write your name on it, and wait for the draw. Then comes the question that stops you cold. What are your chances of winning? The first thought is clear enough. If there are infinitely many tickets, then your single one is swallowed in the crowd. Your chance looks like it vanishes to nothing. Yet when the drawing begins, a ticket must still be chosen. Somebody always wins. The odds for each person are 0, and the odds for someone are 100%. This is the infinite lottery paradox. In a finite lottery, the math makes sense. One ticket out of a million means a 1 in a million chance. But infinity is not just a larger number. It breaks the link completely. Your personal odds collapse to 0, while the event itself remains certain. Think of it like this: a machine filled with an endless collection of numbered balls. Your ball is in there, lost among infinitely many others. When the machine draws one at random, the chance that it's yours is 0, but the chance that some ball comes out is guaranteed. Infinity leaves us holding both truths at once. The paradox also gnaws at our sense of fairness. With an ordinary lottery, the odds may be tiny, but they're real. Here, the math tells you your chance is nothing at all, and yet a winner still appears. Infinity strips the numbers of meaning, leaving behind a puzzle that probability alone can't resolve. It also shows how fragile our everyday thinking is. We often treat infinity as if it were just a very large quantity, a horizon you can always move closer to. But the infinite lottery reveals that infinity is not simply size. It is a shift in the rules themselves. What works with millions or billions no longer works with infinity. And once you see this, the questions multiply. If infinity makes the odds of winning 0, does that mean nobody truly wins? If winning is impossible for each individual, how does it still become inevitable for the group as a whole? The paradox doesn't just challenge probability, it challenges our sense of logic itself, creating a space where certainty and impossibility overlap. You feel the weight of this most clearly if you imagine standing in that hall with your ticket. The crowd is endless. The numbers march upward forever. You know that your chance of winning is exactly 0. Yet you also know with absolute certainty that someone else will win. Hope and hopelessness balance in the same moment, held there by infinity. And the strangeness doesn't stop there, because in an infinite lottery, there would not just be one drawing. There could be infinitely many. Some versions of you might win, while infinitely many others would lose. Infinity doesn't just break the odds once, it breaks them in every possible direction, leaving no firm ground at all. That is the infinite lottery paradox. It shows that infinity doesn't just stretch our numbers, it reshapes the ground they stand on. A simple game of chance becomes a contradiction. A harmless lottery becomes a riddle with no clear resolution. And perhaps the lesson is this: infinity is not just about going further or counting higher. It is about finding the places where our familiar rules fall apart. Even a gamble, as ordinary as a lottery, becomes something alien once infinity quietly steps in. Long before the modern age, when philosophy was still young, there was a man named Zeno of Elea. He lived in ancient Greece more than 2,000 years ago, and he became famous for a set of puzzles that seemed to make motion itself impossible. Imagine you're trying to walk across a room. To get to the other side, you first have to walk halfway. Once you've reached that halfway point, you still need to cover half of the distance that remains. After that, you still need to walk half of what's left, and again and again. The distance keeps dividing into smaller and smaller halves, and in principle, there is no end. There are infinitely many steps between where you stand now and where you want to go. If you truly had to complete every one of those infinite steps, how could you ever arrive? Zeno pushed the idea further with the image of a race. Achilles, the fastest hero in Greek legend, is running against a tortoise. To be generous, Achilles gives it a head start. Zeno argues that Achilles can never overtake it. Why? Because by the time Achilles reaches the place where the tortoise began, it has already moved forward a little. By the time Achilles reaches that new spot, the tortoise has moved forward again. No matter how fast Achilles runs, he is always catching up to where it once was, and the tortoise is always a little further ahead. Of course, in real life, Achilles would blow past the tortoise without breaking a sweat. That's what makes the paradox so interesting. Our senses tell us motion is possible. Our reason, when following Zeno's steps, seems to say otherwise. What Zeno was trying to do was not to deny motion entirely, but to challenge the way people thought about space, time, and continuity. If you can always divide a distance into smaller parts, does that mean there are infinitely many tasks to perform? And if there are infinitely many tasks, how do we ever complete them? Centuries later, mathematicians found a way to resolve this apparent contradiction. The key lies in infinite series. Yes, the distance can be divided infinitely, but the sum of those halves does not grow without limit. 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, adds up to exactly 1. The infinity of steps does not stretch the journey endlessly. Instead, it compresses into a finite whole. So in the case of Achilles, each catching up distance gets smaller and smaller, and when you add them all together, the total is finite. Achilles really does pass the tortoise, just as our eyes tell us. Motion works. The paradox dissolves when we introduce the mathematics of limits. Yet even with this resolution, Zeno's puzzles remain powerful. They remind us that infinity, when applied to the world, is not an easy fit. Our minds are quick to stumble when something can be divided without end. And before the invention of calculus, people had no clear way to handle this strangeness. Zeno's paradoxes survive today, not because they disprove motion, but because they show how easily our reasoning can become trapped by infinity. They force us to admit that the world we move through effortlessly every day hides deep conceptual challenges once we try to describe it with precision. Picture yourself standing at one side of a room again. You take a step, and then another, and then another. You don't freeze in place, you don't get stuck halfway forever. You simply move. And yet, buried beneath that ordinary movement lies a puzzle that baffled some of the sharpest thinkers of the ancient world. That is Zeno's gift, a reminder that even the most obvious things, walking across a floor, running a race, catching up to a tortoise, can turn strange once infinity enters the picture. Imagine stepping into a machine that can carry you backward through time. You pull the lever, the air shifts, and in an instant you're standing years before your own journey began. You might leave a warning for yourself, deliver a message, or hand someone the blueprints for the very device you just travelled in. Already the logic of cause and effect begins to twist because the knowledge you carried backward seems to exist without ever being created. Now imagine not one machine, but an endless sequence of them, spread across past and future alike. Each machine is able to send information back to an earlier point, where another machine receives it and passes it further still, and so on forever. What begins as a single loop of causality spirals into an infinite web of feedback, where no first moment can ever be located. Consider a thought experiment. A scientist in the far future possesses a detailed set of plans for building a time machine. Instead of inventing the design, they send the plans backward. Someone in the past discovers them, builds the device, and eventually sends the same instructions back again. Where in this loop did the knowledge originate? If the process continues infinitely in both directions, the design has no point of origin. The information exists, but the act of creation has evaporated. Another version involves the travellers themselves. Picture a long line of visitors, each arriving one moment earlier than the last, each making a slight adjustment to the past. One traveller nudges an object to the left, the next moves it back, the next shifts it again. By the time you search for the original arrangement, it has been altered infinitely many times, and the idea of a starting state no longer makes sense. The history you thought was stable has been overwritten endlessly, until it becomes nothing more than an infinite blur. The paradox grows sharper the more you try to pin it down. With a single time loop, you can at least imagine tracing the circle, however puzzling it may be. With infinitely many, the structure collapses. Every action is explained by an earlier one, but that explanation only points to something further back, and then further still, with no anchor to stop the descent. It is like following a trail of footprints into the desert, only to realize that the tracks extend forever in both directions, without any first step. Infinity often unsettles by stretching numbers or scattering probabilities, but here it reshapes time itself. Our ordinary sense of sequence, one moment producing the next, the past serving as the ground for the future, falls apart once infinity enters. Instead of time flowing like a river, it becomes a whirlpool with no edge, swallowing the very idea of origin. What makes this scenario vivid is not the mechanics of time travel, but the picture it paints of causality. Imagine machines scattered across centuries, each humming to life, each feeding its output into another earlier machine. The cycle repeats endlessly. You can watch the chain unfold, but the longer you follow it, the less clarity you find. The very abundance of machines drains the story of meaning, because nothing ever begins, and nothing ever truly ends. Some thinkers frame this as a question of information. If knowledge is passed backward infinitely, does it truly exist at all, or is it only an illusion created by the loop? Others see it as a collapse of identity. If infinite travellers each arrive a moment before the last, then no traveller can claim to be the first, and without a first, there may be no genuine act of travelling at all. The infinite time machine's paradox is not really about engineering or physics. It is about what happens when infinity is threaded into the fabric of time. It shows us that time, which we usually treat as the most reliable backdrop of experience, may not withstand the weight of endless recursion. What happens if you add one, then subtract one, then add one again, and keep going forever? At first it feels obvious. Add one, subtract one, you're back at zero. Do it again, and the total never changes. Or does it? Now imagine stopping the sequence not after an even number of steps, but after an odd one. Add one, subtract one, then add one again, and now the total is 1. Go one step further, and it's back to 0. Another step, and it's 1 again. The pattern flickers between the two, never settling down. This strange dance is called Grandi's series, after an Italian mathematician who studied it 300 years ago. It is one of the simplest examples of how infinity slips out of our control. The sum is not 0 and it's not 1. It's both. It's neither. It refuses to answer the question we asked. Later mathematicians tried to tame it. They said, don't look at the sequence at any one stopping point. Look at the way it behaves as a whole. Viewed this way, the sum doesn't stay locked at 0 or 1. It hovers in between. The average value lies halfway, at 1/2. That becomes its infinite sum, not because the numbers actually land there, but because that is the only way to describe their restless motion. And here's the unsettling part. This trick of assigning values to sums that don't converge shows up in physics. In the mathematics of waves or in certain corners of quantum theory, paradoxical series like Grandi's can still yield meaningful results. Numbers that never settle are given interpretations that work anyway. It feels less like solving a problem and more like negotiating with infinity itself. For the ordinary listener, the point is not the technical detail. The point is how quickly infinity makes simple arithmetic turn strange. The series 1 minus 1 plus 1 minus 1 looks harmless, but it hides instability. It never gives you a straight answer. It sits in a state of flicker, balanced forever between two outcomes. And that flicker makes you question something deeper. When we say a series equals 1/2, are we uncovering a hidden truth of mathematics? Or are we imposing order on something that resists being pinned down? Is infinity showing us a real property of numbers? Or is it showing us the limits of our own methods? In everyday life, we like our numbers solid. 1 plus 1 is always 2. Subtract 1 and it's back to 1. That certainty is comforting, stable, and reliable. But infinity bends even this. It says, sometimes the sum isn't 1, and it isn't 0. Sometimes the answer is hidden in the space between, where our rules no longer apply. That's why Grandi's series remains more than a curiosity. It's a lesson wrapped inside a simple string of numbers. A reminder that infinity isn't just large, but slippery. That when you let it into the most basic of calculations, the ground under your feet starts to shift. And maybe that's the real power of this paradox. It doesn't just challenge arithmetic, it challenges the way we think about certainty itself. Even in the simplest patterns, infinity introduces a kind of tremor, a reminder that our neat, reliable world of numbers can turn uncertain the moment we try to carry them out forever. In the late 1800s, the German mathematician Georg Cantor asked a daring question: are all infinities the same size? At first, that might sound strange. Infinity feels like a single concept. Endless is endless. But Cantor discovered something shocking. Some infinities are bigger than others. The idea can be explained with a simple list. Imagine you try to write down every whole number: 1, 2, 3, 4, and so on. The list never ends, but every number has a place. You could, in theory, assign each of them to the rooms of Hilbert's hotel without running out. This infinity is called countable because even though it is endless, you can still move through it step by step. Now compare that with the numbers that exist between 0 and 1, not just familiar fractions like 1/2 or 1/3, but every possible decimal that could fill the gaps. It might seem like these could also be listed one after another, the same way we list the whole numbers. But Cantor showed this is impossible. This infinity is larger. Here's how he proved it. Imagine you try to make a complete list of all the decimals between 0 and 1. You line them up on paper, one below the other, hoping to capture them all. Now Cantor makes a clever move. He reads across the page in a diagonal way, picking one digit from the first entry, another from the second, another from the third, and so on. From those choices, he creates a brand new number. And by changing each digit as he goes, he makes sure this new number is different from every single one already on the list. The conclusion is inescapable. There is no way to make a complete list of all the decimals between 0 and 1. For every attempt, something always escapes. And that means the infinity of decimals is larger than the infinity of whole numbers. This result shook the mathematical world. Until Cantor, infinity was treated as one vast idea, but with one simple construction, he revealed a hierarchy: the infinity of counting numbers, the infinity of fractions, the infinity of decimals, each one larger than the last, and beyond them, even greater infinities still. Not everyone welcomed this discovery. Some mathematicians were fascinated, but others were deeply uncomfortable. The very idea that infinities could come in different sizes was seen as absurd, even dangerous. Cantor himself struggled with the weight of his own work, but history has judged it as one of the great breakthroughs of modern mathematics. For most of us, infinity already feels impossible to grasp. The thought that there are larger and smaller infinities only deepens the mystery. It's like standing in front of a library that stretches endlessly in every direction, and then being told there is another library even larger, and another beyond that, with no final library at all. Cantor's diagonal argument remains one of the simplest and most powerful ideas in mathematics. With nothing more than the concept of a list, he showed that infinity is not a single endless horizon. It is a landscape of different sizes, each one stranger than the last. It's a reminder that when we deal with the infinite, our intuition falters. We want to believe endless means just one thing. Cantor proved it does not. Infinity contains layers upon layers, bigger and bigger, without limit. Imagine a large glass jar on a table. Beside it sits an endless supply of numbered balls. The rules of the game are simple. At each step you add some balls to the jar, and at the same time, you take a few out. The question is, after infinitely many steps, what is left in the jar? To see how this works, picture the process in detail. On the very first step, you drop in 10 balls, numbered 1 through 10, and then immediately remove the ball labelled number 1. On the next step, you add another 10, numbered 11 through 20, and remove ball number 2. On the following step, you add the next 10, and remove ball number 3. And this continues, step after step, carried out forever. At each stage, the jar is filling up with more and more balls, but notice, at every step, the lowest numbered ball is removed. By the end of the infinite process, ball number 1 is gone, ball number 2 is gone, ball number 3 is gone. In fact, every single ball will eventually have been removed, which means that after infinitely many steps, the jar is empty. But here's the twist, if you change the order just slightly, the outcome can be completely different. Suppose you still add 10 balls at each step, but instead of removing the lowest numbered one, you always remove the ball with the highest number in the jar. Now the smallest numbers never leave. After infinitely many steps, the jar doesn't come out empty at all. It's packed with an endless collection of low-numbered balls. Two nearly identical processes, both carried out infinitely, produce totally opposite results. One gives you nothing, the other gives you everything. The Ross-Littlewood paradox shows how easily infinity breaks our intuition about cause and effect. With finite steps, the order of adding and removing hardly matters. But with infinite steps, order becomes everything. Infinity can erase the difference between almost the same and completely different. Philosophers use this paradox to show that infinite processes don't always lead to stable answers. Mathematicians sometimes call them supertasks, where our normal logic collapses because the process never truly ends. It's not just that we don't know the answer, it's that more than one answer can be correct, depending on how the infinite steps are arranged. And that raises unsettling questions. If infinity makes outcomes so unstable, what does that mean for using infinity in mathematics at all? Are we describing something real, or building castles in the air? For everyday life, the jar and the balls are a helpful image. You can picture it. One by one, the numbered balls disappear. And yet, by changing a single rule, which ball you remove, the whole conclusion flips. Infinity leaves no solid ground beneath your feet. That is the strange beauty of the Ross-Littlewood paradox. It reminds us that infinity is not just endless, but sensitive. The tiniest change in order produces outcomes that contradict each other. Empty jar, full jar, both flowing from the same beginning. And maybe that's the lesson worth carrying. Infinity does not simply stretch our numbers longer. It reshapes the very logic we try to apply. In a world without limits, even the smallest choices ripple out into impossible consequences. Step outside on a clear night and look up at the sky. What you see is darkness, scattered with stars. The black of the night feels natural, almost comforting, but there's a deep puzzle hiding inside it. If the universe is infinite, filled with stars in every direction, then why isn't the night sky blazing with light? This question is known as Olbers Paradox. At first, the reasoning is simple. If space stretches out forever and stars are scattered across it without end, then no matter where you look, your line of sight should eventually hit the surface of a star. Just as standing in a dense forest means every view ends at a tree trunk, standing in an infinite universe should mean every view ends at a star. The entire sky should glow as bright as the sun, leaving no room for darkness. And yet when we look up, we see the opposite, a sky dominated by blackness. To picture the puzzle more clearly, imagine space as a vast canvas. If stars were infinite and eternal, their light would layer upon itself, filling every patch of sky until there was no darkness left. Even the most distant stars would contribute, adding their glow to the cosmic backdrop. But they don't. The night remains mostly dark, and that contradiction is the heart of Olbers' Paradox. So what's going on? Several answers combine to resolve the mystery. First, the universe is not eternal. It had a beginning. Light takes time to travel, and the stars we see today are only those whose light has had time to reach us. Beyond a certain distance, their light is still on the way. The night sky is dark in part because the universe has only been shining for a limited span of time. Second, the universe is expanding. As space stretches, light from distant galaxies is stretched as well. Its energy is reduced, shifted into longer wavelengths, fading into invisible ranges of radiation. What might have once been visible starlight arrives to us weakened, stretched beyond what our eyes can detect. The expansion of the universe dims the glow, leaving the night sky darker than it otherwise would be. And third, not every direction contains a star bright enough to see. Space is vast, but stars are scattered unevenly, grouped into galaxies separated by huge gulfs of emptiness. The gaps between them carve the darkness we see overhead. Together, these ideas explain why the sky is not filled with an endless blaze of light. But the paradox still serves a purpose. It reminds us how easy it is to take darkness for granted, and how strange it becomes when we ask why it is there at all. Olbers' Paradox is less about the details of astronomy and more about the way infinity unsettles our intuition. If the universe really were infinite, static and eternal, then the night would never end. Darkness would be impossible. The fact that the night sky's dark is in itself evidence that the universe has a history, that it changes, that it is not infinite in every sense. So the next time you find yourself staring upward on a quiet night, remember what you're really seeing. Every patch of darkness is not just empty space, it is a clue. It tells you that the universe had a beginning. It tells you that it is expanding. It tells you that infinity, once again, reshapes the very questions we ask. And perhaps the lesson is this: what feels ordinary is sometimes the strangest puzzle of all. The night looks dark and simple, but it hides a truth that unravels once infinity steps in. Imagine a trumpet stretching endlessly into the distance. At the wide end, it looks like a simple horn you could hold in your hands. But instead of stopping after a few feet, the horn keeps narrowing and narrowing, tapering off forever without ever reaching a tip. This shape is called Gabriel's horn, named after the archangel who's said to announce the end of time with a trumpet. Here's the strange part. The horn has a finite volume, but an infinite surface area. That means it could be filled up with a limited amount of paint, yet no amount of paint would ever be enough to cover its outside. To see why, picture how the horn is formed. Start with a simple curve on a graph, the function 1 over x. Rotate that curve around an axis, and the surface spirals into a three-dimensional trumpet that narrows forever. If you calculate the volume, the numbers settle to a finite amount. The horn can be filled, but if you calculate the surface area, the numbers refuse to settle. They stretch toward infinity, And that leaves us with the paradox. How can you fill an object completely with a finite supply of paint, but never have enough paint to coat its surface? The inside is measurable, the outside is not. One part behaves like a normal object, the other like a bottomless pit. What makes Gabriel's horn unsettling is how ordinary it looks at first. You can imagine holding the wide end of the horn, pouring in a bucket of paint, and watching as the paint actually fills the endless chamber. It feels possible, almost practical, but the moment you try to coat the outside, reality collapses. No matter how many buckets you bring, no matter how tirelessly you paint, the job is never finished. The surface is always longer, always stretching, always demanding more. It's as if the horn hides two different infinities inside itself, a gentle one that allows the inside to be filled, and a wild one that makes the outside untouchable. Both exist in the same shape, and yet they tell completely different stories. This is why Gabriel's horn lingers in the imagination. It takes something familiar, the outline of a trumpet, and twists it into an object no craftsperson could ever build. It feels like it belongs in our world, yet it belongs only to the mathematics of infinity. And maybe that is what makes it so striking. Infinity doesn't just appear in the vastness of space or the endless march of numbers. It can emerge in the outline of a simple curve drawn on a page and spun into a shape that exists more in thought than in reality. Gabriel's horn is a reminder that infinity does not have to look overwhelming. Sometimes it disguises itself inside something deceptively small and ordinary. And when it does, it shows us how fragile our intuition really is. In the end, this paradox is less about paint or surfaces and more about the limits of what we can imagine. It tells us that even the simplest questions, like how much paint do I need to fill to cover something, can unravel once infinity steps in. Maybe that's the real trick of infinity. It never ends. It just keeps finding new ways to make us question whether we've understood anything at all. We've had monkeys ghostwriting Shakespeare, lamps that can't decide if they're on or off, and hotels that somehow turn overbooking into a spiritual experience. And after all that, I think we've all earned a participation trophy in confusion. This makes me wonder, which paradox melted your brain the most? Tell me in the comments. Now, thanks for watching, and I'll see you in the next one, if we ever escape the loop.